So thank you very much, Uday. So like Uday said, we have been, toying with this idea for some time. In fact, by the end of March, I think that was the first time we got into some discussion about doing this. And like Uday just said, what I thought was that you know we all come from most of us come from the community medicine background, and that therefore it is incumbent upon us that we just understand how this emerging, evolving epidemic can be approached. Just before we begin, though, what I'm doing is as I start this session, I'm muting everybody so that there's no echoes and no disturbances. But if you want to say something as we go along, you can raise your hand, or you can just unmute yourself and just speak into your phone, your device, and we'll try and respond to that. Do feel free to interrupt, do feel free to ask questions as we go along, but there's no protocol here. We're just trying to discuss something as informally as we can. I think almost everybody has seen the movie Jurassic Park. In that movie, there is a very interesting quote that the chief scientist says. He says, "Life finds a way. No matter what, life finds a way, howsoever difficult." What this COVID-19 has done to most of us is that despite these difficulties, despite howsoever challenging scenarios, situations have been, we have found out ways to connect, one of which is this. And we are going to use this opportunity to try to learn something about this mathematical modeling of this. Now, also by way of introduction, we know that we're dealing with a topic that is, hardcore mathematics. So, and we gave up mathematics, most of us gave up mathematics way long ago. So much so that sometimes we get, shivers down our spine when we think of big equations and all that. What I do want to do over this rest of the session is to make sure that that mathematical part doesn't overpower us, but what we get is the concepts, and that the concepts help us to understand the math behind it rather than the other way around. Here is, by the way, so let me start sharing some things. And here is the first thing I want to share. I hope you can see the screen. This is the Johns Hopkins website that real-time updates the numbers from all around the world. As of now, total confirmed, there have been 9 million cases, and global number of deaths is 482,923, almost hinging on to 500,000. So about 10 million and 500,000. So there's a 5% death rate around the world. Now, if we look at, they have it country-wise here. US is number one, of course, we know that, 2.4. Brazil is going very strong, is on number 2 right now. Russia closely following on heels. India is now on number 4, and some time ago India was way back. And if we actually look at the daily cases in India, this is the daily number of cases that are being reported from India, and you can click on this, you can see this. Now the last day, like yesterday, I see that there were 16,000 cases from India, And if you look at this curve, you'll see, I mean, this is still rising. It's going up and up and up. So we have therefore an impending, you know, almost exposure and explosion that is going to happen pretty soon, and we have to deal with this. So I thought that maybe we could just start with a seminar of this sort, maybe, or I don't know what to call this. Maybe this is a seminar, this is a workshop, or it's everything in itself. So I'm going to take help of this PowerPoint presentation as we go along, but that will be basically the gist of it. So this is, I hope everybody can see. I've started to share the screen. If you can't see that, then do give me a thumbs up or something so I know that you can see. Yeah, thank you. So like I said, I thought that this is a good opportunity for us to take the real-time data and understand how epidemics start, and also use this real-time data to come up with some hypothesis testing that we can publish on or understand from. So for that, I thought that let's have this session with specific objectives. And the specific objectives I have for this session are, the session is in 2 parts. And the reason that it is in 2 parts is that the second part is better, or will be better understood if we go through the first part carefully. So in the first part, I'm going to introduce the SEIR model of epidemics, which is the basic block of all the epidemiological models. Then we want to state what a formal SEIR model is. I'm going to introduce a concept of R naught. Then we'll discuss some merits, interpretations, limitations, and inferences from R naught. And then we'll discuss specific COVID-19 models. 2 of which, I mean, there are tons of them available right now, but 2 of those I want to specifically see. Those are the SEIR model and the IHME model, both of which are very widely used. The IHME model is the one that is more commonly used and is very extensive. We'll go through all these models. So that's the part 1, and then in the second part, we're going to try and discuss the geometeorological data that Uday talked about, but that will need an understanding of this part 1. So that's why this session. So let's start with part 1 of this. So the SEIR model is the building block of all epidemiological models for all diseases. It's if we understand the SEIR model properly, we can then build on it, extend it, modify it to understand or to adapt it to specific diseases. But understanding this model in itself is the key to understanding all mathematical models of any epidemic. So the SEIR stands for S for susceptible population, I for infected or infectious population, and R for recovered. Now, the idea behind this model is, and this and its derivatives and such models are actually also called as compartmental epidemiological models. They're so called because we think that at any given point of time, the population can be divided into one of these three compartments. The compartments being, you can either have the disease and are not currently having it, that's a susceptible population, meaning that they are prone to get the disease, but they don't have it as yet. Then there are infected or infectious people who have the infection and are spreading it around. Now, there is actually a semantic difference between infected and infectious, but we'll get to that later. For now, this I group is the one who have the infection and who are spreading it. And then R, those are the people who have had the infection, don't have it now, have recovered from it. And wait a minute. It so happened, let me go to the waiting room. There are some people coming in. I'm going to mute them all. And I'm going to admit one more person. And let's go back to where we were. So these are the SIR models. And in general, we would really like to say that we divide the entire population into these three groups, S, I, and R, and then see the dynamics as to who goes from which group to which group. That's the basis of all compartmental epidemiological models. We're going to start with a game. This is a quick program I wrote to actually explain or demonstrate how the SIR model works. Now, let's say that this grid here represents some geographical area with maybe a little colony with 100 houses, let's say, and this is like a 10 by 10 grid. So there are 100 houses there. Each house has one person. So let's populate that. So when we populate, we will see in a minute that that we have all susceptible people, S standing for susceptible, all 100 are susceptible. Nobody has had the disease, nobody, of course, therefore has not recovered from it. So these are all susceptible people. Now let's say that on the first day of the epidemic begins with one case. So currently the epidemic has not begun. So we see all hundreds are susceptible, no infected, no recovered. So on the first day, there was a random case that occurred here. Can you see this? The I, that's an infected person. And now the epidemic will begin. What I've done is that I've asked the computer to take this effective contact rate. We'll talk about all that, what that means, and recovery time. And these are the inputs I gave it. And based on the inputs, it's going to randomly select who becomes an infection, who becomes a case, who becomes a recovered, and so on and so forth. But the rule is this. On the first day, with this case now, for example, the case is right here. On the next day, or the next unit of time, whatever it is, the cases, the susceptibles who can become cases are only the people who are in direct contact with that case. So there will be this S, this S, this S, this S. So only 1, 2, 3, 4, 5 of these susceptible people have the potential to become a case. Not all of them will become, but they have the potential. So here is a graph of how that's going to look. So this is your day 0, and this is going to through to day 30. On day 0, there were 100. You can see 100 susceptibles, and on day 1, there is this one red dot is a little more, no recovered, and these are the susceptible population, 99. So let's go see what happens on the next day. Now this became infected. This guy became infected. So let's see what happens the next day. And let me go on doing this and try to see how these curves are going to pan out. This, the computer is doing in real time and randomly. So I don't know. And we told the computer that after 4 days, it's going to, some infecteds will recover. So that R that you see, those are the recovered people. They will not have the infection anymore. Let's keep on doing this. And as you see, the number of susceptibles is rapidly falling down because they're getting infected really fast. And those who are getting infected, they are exiting into the recovered class or compartment. And that's how that is behaving. So this random epidemic that I just simulated, now everybody has recovered from the infection. So that was what the epidemic was. So if you can see on this side, they started with 100 susceptibles and they rapidly fell down, and by day 20, nobody remained infection free. Everybody developed it. But the number of active cases or the number of cases simultaneously present at the given point of time, they went on till about 12 days, then some plateaued at around 14, 16 days, and then fell down. And of course, those who recovered, everybody recovered from the infection fine eventually. And so this is basically how an SIR model works. The SIR model is will tell that you start with all susceptibles. The susceptibles will rapidly fall down. The infectious people or infected people will go up for a while and go down, and the recovered people will eventually, replace all the susceptibles. That's an epidemic. So only two parameters we are telling here: how many susceptibles we have to start with, what was the effective contact rate, and what was the recovery rate. These three things decide how the epidemic will pan out in a given population. So that was in terms of a random, experiment. But there is a more, definitive way of doing that. Let's say this is the whole pop. This rectangle, blue rectangle, represents the entire population, the whole population. So what the SIR model says is that this population can be divided into one of the three compartments. So every person in that population can be either a susceptible or an infected or a recovered one at a given point of time. So let's say that we have these 24 balls, each ball representing a susceptible to start with. Now what is going to happen is that we will have a person move, when the person gets infected, move from the S group to the I group. So let's see how that works. See this? So there is one person who got infected and moved from the S compartment into the I compartment. Let's see what happens the next time unit. Another person got infected and moved on. Now when we want to see a third time, what's going to happen is that some of these potentially susceptible cases will become infected, but some of these infected cases will move to the R group, the recovered group, like that. So now as this goes on and on, you will see that, and finally S will all shift to the R group via the I group, and therefore this will go up to 100, this will go to 0, and this will first go up and go down, and that will be what we will call the epidemic. Now, like I said at the beginning of this session, I do want to make sure that we are not, afraid of the mathematical equations and formulae behind this. So I want to walk you actually through these concepts. Let's see a description and then look at the equation. So let's look at only this S compartment for now. So what is happening is that at each time unit, a fraction of the susceptible group becomes infected and they exit the susceptible group. And then this fraction is a function of the number of susceptibles and the number of infected. And I'll explain to you what that means, and the force of infection. Okay, so let's say, for example, there are more susceptibles and more infected people. Then there is a high chance that they will come in contact with each other, and therefore the infection will spread. Now, if there are very few susceptibles and many cases, it is unlikely that the infection will spread that fast. On the converse, if there are many susceptibles and few cases, again there is less chance. It's only when that both numbers are high that there is very high likelihood of the epidemic spreading. So in terms of mathematics, that is represent this, this change that is occurring in the number of susceptibles over a given unit of time is called the DDT. So delta, like change in S over change in the T or the time. So what we can consider that is that this S is the number of people and I is the number of infected, susceptible and infected people. The multiplication of those two is actually going to tell us how infection is going to spread. The larger this product, the faster the progression. Smaller this product, less. Like I just said, if we have more of S and I both together, that's when the infection is going to rapidly progress. Now, we have this term called A. This A is indicating that, let's say, there are two people, one susceptible, one infected, come in contact with each other. Now, that it's not definite that the infection will go from that person to the other person. It's not definite. There is only a fraction of people who come in contact with the case, only they get infected. Not everybody gets infected. So that fraction, that proportion is this A. It's a constant. So we're saying that the number of susceptibles at a given time, the number of infected at a given time, and some constant fraction, these three tell you the change that can happen in S. Now we know also that the only direction in which the change in S can happen is that people are exiting from the S group to the I group. So the number of people in S group will always go on decreasing, and therefore this minus sign. So it will be minus some fraction, some constant, susceptible people and infected people. That's how the S group will change. Now, let's see what happens in this one, the I group. Now, at each time, this same fraction that we talked about of the susceptible group, which becomes infected, they exit from the susceptible group, but they enter the I group, the infected group. Okay, so that's happening the second time. And also, there's another thing happening. Some of the infected people are exiting into the infected, into the recovered group. They recover from the infection and they go out of here and into this. So how will we say this mathematically? The change in the I group is therefore all those people who exited from the susceptible group, they're coming back here. So that minus ASI for S is the ASI for this group, the DDT of I. Minus, because some people are exiting from here to here, some other constant B into the people who are infected. So at that time, suppose if 3 people are infected and 1/3 of them exit, then that means that one person will go from here to here. So DDT of I is basically how many enter from here to here and how many exit from I to R. Then for the recovered group, at each time unit, a fraction of infected, this group, recover from the infection and enter the recovered group, having exited from this group. So What was minus BI here becomes plus BI for the R group. It should not be a problem, right? Everybody okay with this? Okay. So that, this is basically the mathematical formulation of what we were saying in terms of equations. Now, I just wrote another program here to see how the model would work if we use these equations instead of the randomly selecting the experiment that we did. So let's run the epidemic. Now I've asked it that A parameter is 50% and that B parameter is 25%. I just gave some value. You remember from the previous slide that A is the people or the fraction of people who transit from S to I, and B are the people who transit from I to R. So let's run this model. Let's see what happens. Okay, so here's what happens. So S, which was 100 to start with, on the first day, one case came, and then all these numbers were calculated by those equations for every period. That looks like this. If I plot this, it looks like this. So rather than that, jagged curve that we saw the first time around, here is now a much improved, smooth curve that we see for each. The susceptible population would fall down like this because they are exiting and going into the I group. The I group first goes up and then goes down, and the epidemic ends. Here it ended somewhere around 40 days. And the recovered people, they all go up and then they stay. Now, the epidemic, this particular epidemic did not affect everybody. So about 20% or 18% of these people remained susceptible at the end of the epidemic, and therefore only 80 recovered. But the epidemic ended. You might recall from our community medicine, fundamentals of infectious disease epidemiology, that this is called herd immunity. That the epidemic ended because a majority of the portion people recovered and had immunity. So the epidemic could not spread anymore. So this, the other thing to note here is that initially the I is large. This red curve is slightly above the green curve, but then the green curve takes over and goes up. This is because initially there will be infected people who have not recovered, but as we go along, the recovered people will, of course, take up more numbers, and they will be more populous, and therefore the epidemic ends like this. That's the fundamental of any infection. Any infection. You can then fine-tune this model to understand, specific diseases, but any infectious disease has this basis. There are susceptibles, there are infected, there are recovered people. Now we have to remember that this is an oversimplification of the way infectious diseases work. For example, what about, this is not a closed population, and no population in the world today, because of migration and travel and everything, no population is closed. So what about people coming into this population? What about people exiting this population? What about people dying? What about people asymptomatic? 20 different things we can ask ourselves. But those things can be added into this model as we go along. The basis is this. So now there is a Python code. Somebody wrote actually a Python program to do this, and so this is the Python code. This is available. This is the link. If those people from amongst us who are interested in or are conversant with programming, they can also go up, look up this link, and this is what this program does. This is the same curve. now plotted in a different way, but it's the same thing. As you can see, S starts at 1, goes down, stays at some point of time, I goes up and down, and R goes up and stays, stabilizes. So that's basically the SEIR model for you. I hope, so if anybody has questions anywhere during the thing, just raise your hand, unmute, ask. Don't hesitate at all. Because now we are going to enter into a very critical concept of that emanates from this SEIR model. And I know you've heard, each one of you have heard this term, because even the press talks about R naught and everything. But it's not an easy concept to understand, R naught, especially for lay people or people who are not very well versed with the fundamentals of epidemiology. So I do want to take you through this very carefully to try to make sure that we all understand this. I'm going to revisit the SEIR model again now, and we'll try and understand some terms. So we said that there is a susceptible compartment, there is an infectious compartment, there is a recovered compartment. We also said that the susceptible population transits into infectious population at the rate ASI. Okay. Now I know that in those equations earlier on we wrote ASI, but that was to indicate that S and I together decide the rate of transmission. But let's think it a little more. S is the number of people and I is the number of people. So people into people become people squared mathematically. How can people transit into people squared? It cannot happen. And therefore, the correct equation is to actually divide it by n, which is also people, n meaning the number of people to start with. And it's actually a sum of susceptible, infectious, and recovered at any time, because that number is going to stay constant. So the rate of transit is not actually ASI, but it is ASI over n. Now it is people. People into people divided by people, so that's people. So A is that fraction that we were talking about. Then we have infectious people transiting into the recovered group at BI rate, right? So this I is the number of infected people, B is the rate at which they go into this. Now this A is also called as, some people refer to that as beta. This is just confusion, but that's how it is. That's life. I can't help it. So some people call this A as beta, and that A basically represents the fraction that will be converting from susceptible to infectious, or the fraction that is basically transmission of the epidemic. And therefore, it's called the transmission coefficient. So this A is basically a transmission coefficient. So what will we call the B then? Okay, by the way, some people call it gamma. And that represents the recovery coefficient, because that's the rate at which infectious people recover. So we need to remember these two terms: transmission coefficient, recovery coefficient. Transmission is that fraction of susceptibles that converts into infectious, and recovery is that fraction of infectious that converts into the recovered. So conceptually, here is the model, the SEIR model in mathematical terms. Where you see a dot at the top, it is the same as writing ddt. So it is the same as writing rate of change. So the rate of change of S is minus, because they are exiting, minus ASI over N, this thing. The rate of change of I is ASI upon N, this thing that is coming in, and minus this thing that is going out, BI. And the rate of change of R is BI. That's what an SIR model looks like. But because some people give it different names, you can also write it as S is equal to minus beta SIN over N, that is. I dot is beta SI over N, and gamma is minus gamma I, and R dot is gamma I. This is the same thing. Where there is B, there is gamma. Where there is A, there is beta. But it's the same thing. That's what an SIR model is. So whenever mathematicians speak about SIR model, they look at these three equations, because that describes how an epidemic will pan out. Let's do some quick arithmetic. It's not very difficult. So here are the facts. We always start with S equal to N. All total people are susceptible to start with. There's no infected, there's no recovered. These are the assumptions of the model, okay? Always remember, the epidemic begins with one case, and hence at time t0, S is equal to N minus 1, I is equal to 1, and R is equal to 0. This should be very straightforward. Those are the facts. Now here is a little bit of imagination. Let's say that N is very large, like 1 million, 10 million, however, like large population we're talking about. Now, when the population is that high, this N minus 1 that we're talking about mathematically is not very different from N. This is almost equal. If you just subtract 1 from infinity, is it still infinity? So let's remember these two things, facts and imagination, and let's simplify the SIR model with this information. So I dot or I not meaning at time 0. So the number of infected at time 0 is 1. So there should not be any issue with that. And the number of infected at time 1, which is the next time unit, we know is that thing called A, that transmission coefficient, multiplied by those who were susceptible at time 0 and those who were infected at time 0, divided by the N, because this was that ASIN thing, minus B, which is a constant, which is the recovery constant or coefficient, multiplied by the number of infected at time 0. Any issues with this? So now here is the fun. We know that I naught is 1, right? So here in this equation, if we put I naught equal to 1, it simplifies as A S naught over N minus B, because this I naught is 1 and this I naught is 1. So S naught, now S naught we said is N minus 1, and because N is large, we said that is almost equal to N. Put these values in this equation and see what we get. I1 is A multiplied by N, because S naught is almost N, multiplied by 1 because I naught is 1, divided by N because this is N here, minus B. So this is saying N and N gets cancelled, 1 remains 1. So this is basically A. All this entire thing is just A. So you end up with a simple equation, A minus B. It's just A minus B. How many people or what fraction of people get infected, what fraction of people recover. Just a difference of 2 is what the number of people who will be infected at time 1 when N is large. Now that's the equation to remember. I dot 1 is equal to A minus B. Very simple. So let's do a trick now. Let's divide this equation, this entire equation, by B. So what we can say is I dot 1 divided by B is equal to A minus B divided by B, and see what that happens. Just arithmetic, simple basic arithmetics. What we get is A upon B minus 1. Now you might ask me why we're doing all this. It'll become clear in a second. This equation divided by B can be written as A upon B minus 1. But I don't want that to be divided, so I remultiply it by B. Now again multiply, so what I get is I1 divided by beta and multiplied by beta is, or B is the same thing, so I1 stays, and I multiply this side with B, I get B into the bracket A upon B minus 1. To bring this into perspective, this is people infected at time 1, and that is nothing but people who can recover from infected to recovery, multiplied by the ratio of those who can, those susceptibles who become infected divided by those infected who become recovered, minus 1. And now we'll see why this is important. Just try and, imprint this equation into the mind, and let's go forward. So let's go forward. This is a very important equation to remember, so that's why that was done. See, come now to the concept of the basic reproduction rate, or the R naught. That ratio A over B, alternatively called as beta over gamma, is the ratio of transmission coefficient and recovery coefficient. Those who can get infected versus those who can recover, upon those who can recover, and that ratio is called R naught. This is the name for that, the official name for that is basic reproduction rate. This is the rate at which the epidemic is reproducing itself, or the infected people are reproducing it themselves. This reproduction is why it is called reproduction. It is a very weird word to use in an epidemic. Why it's called reproduction is because when this parameter was first developed, it was borrowed from population, demographic field, and in demography, it's similar. It's called reproduction rate, and it's for want of a better name, they just stayed with that name, basic reproduction rate. The person who developed this actually called it generation rate, because it's the next generation of infected people, and how many people can be generated from the one generation before it. But everybody calls it basic reproduction rate. It stayed like basic reproduction rate. The name is not more important. The concept is. The concept is this. So it can also be interpreted as the ratio of secondary to primary infections. In other words, how many persons does a single case give the infection to? How many secondary infections result from one primary case? That's what an R naught is. It's also, as we just saw, ratio of recovery to, transmission to recovery. It also tells us the transmissibility of the infection. How transmissible is it? Is it going to quickly spread, or is it not? It's an indicator of quickness, and it can indicate effectiveness of a potential public health interventions. And we'll deal with all these, how it does. But before going there, I do want to bring to your attention a paper that was published in Emerging Infectious Diseases 2019, just last year, by Delameter et al. And they've explained, the title is this: Complexity of the Basic Reproduction Number. It is complex, because, and it is, if we just read this out, this abstract, we'll know what the difficulty is. The basic reproduction number are not also called the basic reproduction ratio or rate, or basic reproductive rate, is an epidemiologic metric used to describe the contagiousness or transmissibility of infectious agents. R0 is affected by numerous biological, socio-behavioral, and environmental factors that govern pathogen transmission, and therefore is usually estimated with various types of complex mathematical models, which make R0 easily misrepresented, misinterpreted, and misapplied. R0 is not a biological constant for a pathogen, or a rate over time, or a measure of disease severity, and R0 cannot be modified through vaccination campaigns. R0 is rarely measured directly, and modeled R0 values are dependent on model structures and assumptions. There's so many problems with using R0. Some R0 values reported in scientific literature are likely obsolete. R0 must be estimated, reported, and applied with great caution because this basic metric is far from simple. Even though it's called basic reproduction rate, it's not as basic as it seems. So we really have to know this, what this is, to be able to write papers based on this. There are three definitions I wanted to take through quickly. One is that method by Diaz, definition by Diaz. He says that this is the number of secondary cases one case would produce in a completely susceptible population. Then Paul Fine added this word. It is not the number, but it's the average number of secondary cases. And then Dickman et al., they said it's the expected number of secondary cases. But I mean, these are refinements. But basically, the idea is it's a ratio of secondary to primary. So here is the interpretation from RO. Remember this equation again. I dot is B multiplied by ratio A over B minus 1. So if we substitute this symbol R naught for A by B, then we get I dot is B into R naught minus 1. Now this is very important. If we look at this equation, so there are some people waiting. I'm just admitting them right now. And there is some chat going on, and did I not admit? I did admit somebody, whosoever was waiting. I think I did add. So let me admit all again. All right. So getting back to this equation, what we see here is that everything really depends on the relationship of this R naught to this 1 in this equation. If R naught is greater than 1, then this number will be positive. We know this B is positive, so positive multiplied by positive will be, positive. And therefore, the secondary cases will increase with time. And then there is an epidemic whenever R naught is more than 1. When R naught is equal to 1, there is no new cases added. So whatever cases were there will stay. That's when an endemic occurs. The cases stay there. There's no epidemic. And when R naught is less than 1, the disease will just die out. So here are those three curves representing those. So if R naught is 2, for example, that is each case is giving it to 2 people, then what we see is an epidemic curve going steep up like that. If R naught is 1, it's a stable curve like this. And if R naught is less than 1, goes down like that. That's very important because this is going to tell us when an epidemic will or will not prosper. So let me, from the literature, report some of the R naught values. The seasonal influenza that we have. It's a droplet infection, we know. And the R naught for that is, variable, because we know that the seasonal influenza is in, various strains. This is not fixed, therefore, and R naught therefore varies between 0.9 to 2.1. The 2009 swine flu was had an R naught of 1.4 to 1.6. Cholera, waterborne, has an R naught of 1.7 to 2.6. The hepatitis, Ebola, and HIV, which are basically transmitted through body fluids, they have rather high R naughts, 2 and maybe 4 here. The 1918 influenza pandemic had only 1.4 to 2.8. Smallpox is 3.5 to 6.0. Mumps was from 4 to 7. Pertussis, 5.5. That's every case gives it to 5 or 5.5 secondary cases. But look at this, measles, 18. Measles epidemics are very rapidly, they spread like wildfires. The good thing about measles epidemic is, though, that once a clinical disease, lifelong immunity. So they spread, but their the death rates and those are not very very high because of the immunity, and there are no secondary infections. By secondary infections, I mean in the same person. So let's look at some of the problems with R naught. Now there is a 2080 rule of infection spread. Let's say these are the infectors. 5 infectors, 5 primary cases. Now let's say that they gave 10 secondary cases. So the R naught was 2. But see what happened. What actually happened was that this number 2 infector gave the infection to 8 people. Number 4 gave it to 1, number 5 gave it to 1, number 3 and 1 actually did not give it to anybody. So this guy is the one who actually took the whole thing to 2, right? These 2 people are not transmitting the infection much, and these people did not transmit at all. So the 2080 rule says that in most infections, 20% of the infectors end up infecting 80% of the infectees. So conversely, 80% of the infectors transmit the infection to only 20% of the infectees. These 20% people who do the bulk of transmission, they are called super spreaders. These people are the ones that we look at. We always discuss whether lockdown and these big things, big public health measures are really required. For example, in SARS, there was a hotel lobby that was identified to be a super spreader. And if the infections are identified early and the infectors who can be super spreaders are identified pretty quickly, then you can stop the majority of infections or the epidemic. So not every epidemic really requires lockdown if you are able to identify these super spreaders. There is this very nice paper by Klein that explains what are the types of or factors or determinants of super spreaders. They can be host related, they can be pathogen related, they can be environmental related. Those from community medicine will know this is what we have always called the epidemiological triad. And these factors can be physiological, they can be behavioral, genetic, immunological, virulence related. We'll not go through the details of this, but I'm leaving this in just so you can go find afterwards what are the factors that can lead to super spreaders. But the problem with R naught is, the first problem that we saw was it's an average, but it doesn't describe the variability of transmission. The second thing is that it's time dependence. When in the earlier phases of the epidemic, the cases are increasing and the R naught is high. But the latter part of the epidemic, the cases are decreasing. So R naught becomes small. You remember this figure from previous slide? R naught of 2 is increasing, R naught 0.5 is decreasing. And if you just combine these two curves, we get this type of thing. So R naught is actually increasing up in the first part of the epidemic and decreasing in the last part of the epidemic. And therefore, to actually get the average R naught over the entire epidemic, we have to wait till the epidemic is over. We cannot estimate the R naught, before that. So after the epidemic is over also, R naught represents the average number of secondary cases per infector that we saw previously, but also averaged over the duration of the epidemic. So it's a lot of averaging that is going on. It's too much summary and too much simplification. So here is a quick example of that. The third problem with these kinds of metrics called R naught. There is in South America, there is an island called Tristan da Cunha, and this is an epidemic of that occurred in Tristan da Cunha in 1971. There was a ship called Tristania that came there. The island was very small, 284 people only. But by the end of it, 273, 96% of the people were infected. But if you can see this is directly from the paper by Mantle and Tyrrell, who actually reported this in 1973. You'll see that there is a primary peak, then there's a drop, then there's a second wave, and then went on. Now the problem is, how do you calculate R naught for this? So when there are multiphasic epidemics, there could be, multiple viral agents, there could be mutations in the virus, there could be some people spreading it as a second wave, and R naught is not descriptive in such situations. So we should not use R naught in such situations. And from conceptual point of view, I do want to give a quick run through this timing thing, because timing is very important. Let's say this line represents the time, and let's see what are the events that occur in the context of an infection. First, there is exposure. Then the infection is developing within the body, but the person is not infectious in the sense that they are not spreading or shedding the antigen or the micropathogen. So this time there's nothing there. Then symptoms come, and finally recovery occurs. So in our epidemiological terms, this period starting from exposure to start of beginning of shedding, that's what's called the latent period. Whereas the period from exposure to symptoms is called the incubation period. In incubation period, therefore, we'll have people who are asymptomatic, but they are infected. And the period of infectiousness is basically start of shedding to end of shedding, which is recovery. Now let's say that this was the timeline in an infector, a person who was infecting. And so the person gave the infection to a secondary person called the infectee, and the same timeline came. Now this timeline will of course be a little later than this, because the infection has progressed from infector to infectee. So here you'll see from a public health perspective, there is one time interval that is very important, and that is a time interval between the start of symptoms of the infector and the start of symptoms of the infectee. This is a very important period of time. This period is called the serial interval, or it's called the generation time. Now, this generation time is very important because this is where the generation of the epidemic actually happens. And the longer this generation time, the longer the transmissibility, because more people will come in contact. The shorter this generation time, the lesser the transmissibility. And that's the same as to say R naught is therefore directly proportional to the serial interval. And we have to understand this because, especially in the context of COVID, this is very important. So the rule to remember is that serial interval is of importance in estimation R naught, and we cannot just jump to that. I do quickly want to show you a package that does this, and so what I'm going to do is escape from here, and let me start an R session and very quickly show you that. So I am now going to start sharing the R session. I don't want you to be too much worried about that, but I do want to show you. So there is a package called R naught. It's and you know, people who have worked in R, it's publicly available, it's free, everything is free, you can do it yourself. So I just loaded that package called R naught, and that package does it. So they have given some data sets already, and they have a data set called Germany.1918, which lists the number of cases of influenza 1918 influenza pandemic in Germany by date. And so let me actually show you how that graph looked. Those who don't know R, don't worry about this. Just look at the result. So this is what the result is. This is the epidemic. This is the number of cases. And if I just show you what that data is, this is the data. So they have the dates, and on each date the number of cases that were reported of influenza. So let's use this R naught package to actually estimate the R naught. Now there are various methods, and I don't need to go into the mathematics of all those, but let's say R naught was estimated using a maximum likelihood method. est.r0.ml for that, and I'm going to use the Germany data. Oh, but there's one thing I got to do before that. That is that I have to tell this program what is the generation time. We just saw that generation time is important for estimation of R naught. Now, for the influenza pandemic, this influenza pandemic, 1918 pandemic, the generation time was had a mean generation time of 3 days. So if let me generate a variable called GT, which is basically generation dot time is a function within that package, and we have to tell what distribution it follows. But I don't want to you to go into all that, but just want to tell you that it has a mean of 3 days and a standard deviation of 1.5 days. So I'm going to tell that to this program. So the program now knows that the generation time is that. And so let's see what the R naught for this would be. R naught is very easy to calculate. Estimation of R naught dot ml for maximum likelihood using the Germany dot 1918 data and GT as the generation time. So it has done that. Now, let me ask it what calculation it has done. So it's telling me that the R naught was estimated to be 1.26 with that confidence interval for this particular epidemic. 1.26 is not that big, but we know millions of people were infected and died. That's because everybody was susceptible, just as the case is in COVID disease for now. So we can do this similarly for our data set, and that's what we've done. We'll come back to that a little later. Now what I'm going to do is get back to the PowerPoint presentation and continue from where we were. Now, as if the SEIR model was not complex enough because it's considered to be a basic fundamental, there is another model called SEIR model. See, let's consider the example of tuberculosis. Let's say we want to generate a model for tuberculosis epidemic. Now, we know that once a person is infected with mycobacteria, the person can stay infected for a long time with no symptoms, no disease, nothing. Long time meaning even decades, 20 years, 30 years. They will have the bacteria within their lungs or their body, wherever they are. Nothing will happen. The bacteria will be just dormant, sitting there in the body. So that, when the latent period is that long, which is the latent period, again to repeat, is a period between exposure and starting shedding. So they're not shedding the bacterium, nothing is happening. The bacterium is just there. Now then, those people who have that bacterium but are not shedding it are not epidemiologically important because those are not contributing to the epidemic. It's only those people who will shed the bacterium or the virus. Those are the ones that are important. And therefore, we now add one more group of persons. So the infected now become split into two groups: susceptible, exposed, but not infectious. Infectious, that is spreading, and recovered. So that SIR model now becomes an SEIR model. And this was our new group, exposed group, and this is that model. Now there is one more parameter added here, CE, but the logic is still the same. And I don't want you to go into all these details right now, but the idea is for me to tell you that the SEIR model is a little more sophisticated than the SIR model. So this is a paper. This is from medRxiv. This paper was published by this group from China, Peng, and they developed this model. Now you'll see the model is a lot more complicated than what we have been dealing with. There is S group, E group, I group, R group, and for each of them, quarantine is now added. So there is an S group that is quarantined. There is an E group that is quarantined, and there is an I group that is quarantined. And they're calling it SQ, EQ, and H. And then there is also a group that receives some treatment, because these two groups are just quarantine or observation. This is a group that is quarantine and treatment. So this is a pretty complex model. And now they have these arrows telling us who goes from where to where. And they came up with this group of differential equations for the entire model. And look at the results they got. People who got cured and people who got infected or remained infected. These dots that you see are the actual data, and these red lines that you see are what the model is predicting. So why is this important? It's because we now understand that we should take the SEIR model to much more details and much more complexity to be able to accurately predict what is happening. And you all know that IHME model is the model that White House uses, that everybody uses now for prediction. The Institute of Health Metrics and Evaluation. How many of you know the Global Burden of Disease study led by this phenomenal researcher, Dr. Murray? He is the director of IHME, and they developed this model. It's also in a repository, and I'll quickly want to show you what that model is. And let me just see which this is SciPy. This is mainland China. Lackman. Okay, so what we can do is basically do this. Let me go to the presentation. Let's just go from there. Okay, so can you all see this this model? So this is the entire model. So in you can define the population, you can give the epidemiological parameters, you can give interventions, and you can see what will happen here. For example, let's say you can choose the age distribution of let's say India, and confirmed cases, because it has direct access to the worldwide reporting. Let me choose if there is anything India. India, Maharashtra. Okay, and here is the intervention. So they know when the intervention began. This is 25th of March when the lockdown began. So they're saying that that's the intervention that began. Before that, the R naught was 4.53 according to them, and after that, it came down to 0.95.
Hemant, we can't see. We are only seeing Institute of Health Metrics on your
you cannot
screen.
Okay. Let me just stop share and let me just start share again. Okay, this is the one. Perhaps I did not share that that one. Can you see now? Okay, so so this is the model I was talking about. I think I believe you are able to see that now. So I just chose India and India, Maharashtra, and this was what I was showing. Excuse me. And what I find is, this is the R naughts, and then they're giving me, all the details. What are the cumulative cases by data? What are the cumulative cases by, at that time point, like at this time point? For example, let's say 17th of April. They say on that day, the cumulative cases were 3.32K, weekly cases were however many, and etc. So that's the model I wanted to show you, because this is in pretty details, and you can actually go visit this link and play around with it. So let me take you back to the PowerPoint presentation. So those are the two models I wanted to run by you.